Hi folks, welcome to the last part of this week's lesson. So we're going to go back to our old friend Broccoli Bear. And remember that Broccoli Bear started off, he could only travel in one dimension, so back and forth. And so, working with a number line with some point of reference was enough to describe any motion problems. Okay, but then Broccoli Bear decided he wanted to start traveling on the ground in two dimensions. And so we had to bring up this idea of vectors to describe motion, because positive and negative wasn't enough to describe direction. All right, so now what if Broccoli Bear, though, wants to, maybe start climbing trees, maybe build a rocket, build an airplane? So what if Broccoli Bear wants to live in three dimensions? All right, so let's see if we can find Broccoli Bear. Oh, there's Broccoli Bear, and Broccoli Bear is now not limiting himself to just traveling on the ground. He can travel in three dimensions. Okay, so the question is how do we describe, even say something like position, in three dimensions? Now, there is a way to do it that's similar to what we did in 2D, in other words, using angles. Okay, and this is actually often used in astronomy. So I can, decide, okay, I'm going to look at north, say that's north, and I'm going to say, well, I'm going to take, an angle moving counterclockwise from the north, then a second angle of elevation, and then the distance away will be my third piece of information. So notice we need two pieces of information to describe something three pieces of information to describe something in three dimensions. So we can use two angles and then a distance away. Okay, but I want you to just imagine for a second trying to solve problems of adding vectors using these types of definitions. Okay, and that starts to get a little too complex. Okay, so we're actually going to reconsider how we look at this idea of a vector. Okay, so let's go back to our other screen here. Okay, and let's think about what we did in one dimension. Okay, so we used the number line and we had Broccoli Bear, move back and forth. Okay, well, we have a similar way of describing position in two dimensions that we haven't had to use at this point. But of course, we've got the Cartesian plane in two dimensions that allows us to describe position based on this grid system, based on these x and y axes. Okay, so what we're going to do is we're going to start thinking about position in three dimensions using a three-dimensional Cartesian coordinate system, meaning we don't just have the x and y axis. So this would represent, the ground, just our regular two-dimensional Cartesian plane. We're now going to add this third axis. Okay, so if we want to describe Broccoli Bear's position in three dimensions, well, you would get an x component, a y component, and then a z component going upwards. Okay, so we see that these number lines are all mutually perpendicular. X is perpendicular to y, and they're both perpendicular to z. Okay, so similar to what we have in our two-dimensional Cartesian system. Okay, now we do have to figure out how we're going to place these. Okay, so we know that when we're in two dimensions, we just place the x-axis horizontally and the y-axis vertically. So here, there's a system for how we place these axes, and it's called the right-handed system. Okay, and the way it works is wherever the x-axis is you place your fingers in the x direction. You bend them over, so this is with your right hand, you bend it over, and once you bend over your fingers, that's going to be the y direction, and then your thumb pointing upwards is going to be the x direction, so z direction. So x, y, z, and it's called a right-handed system. But of course, we can't always go around carrying this 3D Cartesian system. All right, and we can't exactly, sort of hold a point out in space and have it just stay there. We don't have access to holograms, so we're going to have to find a way to describe this system using a two-dimensional piece of paper. Okay, and let's see how we can do that. All right, so what we're going to do is we're going to draw this system, okay? And you notice here how this x-axis is at an angle, because what we're trying to do is we're trying to create a sense of perspective, okay? What you have to imagine is that this y and z is on the ground, and this x-axis is sticking out of the paper, okay? So essentially what we have is we have the x and y axes are here, sorry, the y and z axes, okay, try to make them perpendicular to each other, and the x-axis is sticking out, okay? So this is what we're trying to represent, okay? So we use that angle on our diagram to show that x-axis coming out, and then the y-axis, and then the z-axis. So that's what we're trying to represent with this diagram here, okay? So if you're trying to describe a point in 3D, but again on this two-dimensional piece of paper, what we use to give that sense of perspective is we don't just draw a point, which is going to be very hard to distinguish where it is in 3 space when you're drawing it on a 2D piece of paper, is we use this idea of drawing a rectangular prism. So let's see what this represents. This 0.624, so again, it's an ordered triple instead of an ordered pair. So x, y, z. So what this is saying is that I'm going 6 units in the x direction, 2 units in the y direction. But look at how I'm moving. When I'm moving in the y direction, I'm moving parallel to the y-axis, like you would on a Cartesian plane. And then I'm moving 4 units up in the z direction, so parallel to the z-axis. So parallel to the y-axis, 6 units, 2 units, and 4 units up. Now notice here, if you go to the z-axis, this represents the value 4 on the z-axis, but I am going up 4 units from this point, okay? And then from there, we can draw this rectangular prism to give us the sense that the point lies somewhere in this region here on the positive side of x, the positive side of y, the positive side of z. Okay? Now, where would negative x be? Well, you would just continue the line backwards. Where would negative y be? You would just continue the line that way. And where would negative z be? It would be below, continuing the line there. Okay, so let's take a look at the notes. So this idea of 3 space, or Cartesian 3 space, which we denote R, we say R3, we don't say R cubed. So that means the Cartesian plane would just be R2, and the number line would be R1. Okay, so again, similar to our Cartesian coordinate system, we have an ordered set of numbers, except now there's 3 of them. Okay, and the axes are mutually perpendicular with this right-handed system. Okay, and if you want to try to plot a point in 3D, the best thing to do is to use this rectangular prism. So I'm not going to have you draw, I might have you draw one of them in the assignment, but it's not something that we're going to spend a lot of our time doing, because hopefully I'll actually give you what the major goal is in the next little bit, is to see if we can find a way to work with vectors that doesn't rely so much on the geometry that we've needed to use up until now. Okay, so let's do an example. I'll just show you what this would look like here. So let's assume everything goes up by 1. Okay, so I want to plot the point 2, 3, 4. Okay, so here I'm going to start at 0, 0, 0, and I'm going to go 2 in the x direction, and then I'm going to go 2 in the y direction. But remember, I want to travel horizontally, so I want to travel in this parallel to the y-axis. Okay, 3 units. So you see what I'm going to do is I'm going to create this parallelogram. It's actually a rectangle, because remember, the angle here is 90 degrees. It's going to look like a parallelogram, but really represents a rectangle. Okay, so there we go. This represents going 2 in the x direction, 3 in the y direction, and now I have to measure 4 in the z direction. I'm not going to go crazy doing that, but let's see if I can be as accurate as I can. So there's 4 to about there. So I'm going to go to this point here, and it looks like 4 units upwards is somewhere there. And there's my point. But that's not very, let's see if I can maybe do this in red so it looks a little better. Okay, there's my point. Okay, so I'm going 2, 3, and then 4. Okay, but again, not very convincing. So what I'm going to do is I'm going to create my rectangular prism. I'm going to go up, okay, and then 1, 2, 3, 4. Not the best job here, but this gives us the impression that it's at the, so if this is 0, 0, this point 2, 3, 4, point P, is on the other diagonal, on the other corner of this rectangular prism. All right? So this is how we draw points, and you can see that this is not the easiest thing in the world. So we're going to have to hope that I'm right, that a lot of what we do now in 3D is not going to depend so much on having to draw the points exactly. In fact, hopefully it doesn't have to involve drawing anything precisely at all. All right, so if we want to avoid this idea of using angles to describe vectors, okay, well, we're actually going to take a whole different view on the idea of vectors. All right, so let's go back to our diagram here. Okay, and we're going to consider our number line, okay, which we used a little earlier on, or even in the last course, to describe direction. Remember, in one of the first lessons, I thought of this, we talked about this idea of talking about numbers as vectors. In other words, instead of talking about the number 4, we're going to talk about the vector 4, the vector that starts at 0 and ends at 4. And this behaved a lot like the number 4, you know, and this would represent the number 6. And we saw that we could add these by placing them tip to tail. Okay, and this gave us, in fact, our inspiration for how to define additions of vectors in 2D. Okay, well, we're going to take this one step further. We're going to use, again, number lines to define vectors, except now we're going to use them in 2 dimensions. Okay, and our new way of defining vectors is to define a vector as starting from 0, 0 and ending at some point. Okay, so this vector here, say this x value is a and this y value is b. Okay, we see that this vector starts at 0, 0 and ends at the point AB. And this is how we define this vector. Okay, now we need to give this a name. Well, since we're defining the vector as always starting from 0, 0, well, guess what? We're actually going to define the vector as AB in these round brackets. Now, if you remember a long time ago, I told you that this symbol was going to mean something else, because originally this meant the point AB for you. Then, of course, we use this notation to represent the interval from number A to number B, not including A and B. Well, this is going to be our third meaning for this symbol here. This represents the vector that starts at 0, 0 and ends at the point AB. So if, say, this scale goes up by 1, goes up by 1, this vector that starts at 0, 0 and goes to 1, 2, 3, 4, 5, and 3, so that goes from 0, 0 to the point 5, 3, is actually also called the vector 5, 3. Okay, now you might say, oh, this might be confusing, but it's all about context. If we're talking about a point 5, 3, then this represents a point. If we're talking about the vector 5, 3, then it represents the vector. Okay? Now, this is one thing you have to keep in mind, is just because we're defining the vector starting at 0, 0, we can still move it around. This still represents the vector 5, 3. Because if I were to place it at the origin, remember, vectors are movable, it would still have an x value of 5, a y value of 3. All right? Now, there's a bit of an issue with defining a vector this way. Okay? When we were talking about vectors previously, we thought of a vector as, well, I give you the magnitude, and in some way I'm describing the direction very explicitly. So maybe using a cardinal system, north 20 degrees west, okay? Or two vectors that are 30 degrees from each other. So right away we're going to deal with the first problem, is the way in which we define vectors, what we call algebraic vectors. We don't know, just by looking at it, what the magnitude of this vector is, and we don't know what the direction is. I guess in my mind I could imagine, well, it's further in the x than it is towards the y, so it'd be like less than 45 degrees from the x-axis, but we don't have those two things given explicitly. So that's a big loss here. So we have to hope that what we gain in defining vectors this way will make up for the fact that we are not able to get the magnitude and direction just by looking at it. We're going to have to do some work. All right? So, now the reality is we could get away with not defining vectors algebraically in 2D. Okay? There's a lot of nice things about it, we'll see. But where we really gain in using this method of defining vectors, as we're going to see later on, is defining 3D vectors this way, because we define a 3D vector in the exact same way. All right? By defining it as a vector that starts at 0, 0, 0 and ends at the point ABC. That now becomes the vector ABC. Okay? So yet again, you see how we're using the rectangular prism to sort of locate our point, to give that sense of perspective. And now this becomes the vector ABC. All right? So again, like I said, hopefully we'll see that this is all worthwhile, that losing the ability to see the magnitude and direction explicitly will be a good trade-off. Okay, so the last thing we're going to do is we're just going to look at the basics of a vector, and that's the magnitude and the direction. All right, so let's take a look at 2D vectors here. Okay, so if I take the vector 4, 5, so we'll assume that goes up by 1, goes up by 1, so 1, 2, 3, 4, 1, 2, 3, 4, 5. So the vector that goes from 0, 0, 2, 4, 5, there you go. There's my vector 4, 5. Okay, and here if I want to draw this vector, negative 3, 5, so 1, 2, 3 in the negative direction, 1, 2, 3, 4, 5. There's my vector negative 3, 5. Okay, now let's see if we can find the magnitude of this vector. Okay, well, this is where we realize that hopefully you're seeing that, hey, wait a minute, if I've gone 4 in that direction, it means this horizontal length is 4 and this vertical length is 5. If I consider this right angle triangle, I realize that I can just use Pythagoras to determine the length of this vector. So the magnitude of the vector 4, 5, okay, is just going to be equal to, well, the square root of 4 squared plus 5 squared. Now, if I look at this vector here, negative 3, 5, okay, well, if I break it up into this triangle, well, this length is, well, 3, and this is 5. So the magnitude of, the magnitude of the vector negative 3, 5 is just going to be, well, the square root of 3 squared plus 5 squared. But when you think about it, because I'm squaring this number, it actually doesn't matter whether I use 3 or the actual x component, negative 3. It's the same as writing negative 3 squared plus 5 squared. So here we realize that whatever this value is, say it's not negative 3, 5, say it's any 2D vector AB, you realize that you can define the magnitude of a 2D algebraic vector as just the square root of the x component squared plus the y component squared. And it makes no difference whether this whether the a and or b values are negative, because you're squaring them. Okay? So in fact, we've already answered part of the question that's coming up next. So there we go. Now, remember what we said. Having a vector given in algebraic form doesn't give you the magnitude explicitly, but we're seeing that the magnitude can be found relatively easily when we need it. Okay? So let's draw the vector. So notice here, why is this the vector? Because they tell me it's a vector. Okay? So let's see if we can draw this one here. So here, the x component is negative 2. So that means I'm going to go 2 in the other direction, negative 2. And then the y value is 2. So remember we said we're always going to travel parallel to the axes. Okay, and now I have to go 3 units down. So there's my 3 units in the z direction. So it takes me about there. Okay, and now we can draw our rectangular prism. So go down to 3. There we go. There we go. There's that one there. You can even take this down. Okay, and so now we're drawing the vector negative 2, 2, 3. So we're not just drawing the point. That's the point, negative 2, negative 2, negative 2, 2, and negative 3. We want to draw the vector. So that joins 0, 0, 0 to that point. Okay. Now, some people ask, well, do I have to draw the rectangular prism? Well, yes, because that really does give a sense of exactly what the x, y, and z values are. If you don't draw it, it's very tough to see what point this end point represents. Okay? So, let's take a look at the direction of a 2D algebraic vector. Well, this is where, you know what? Why don't we just recycle what we've already had? Because we've already worked with direction or angles in a 2D context, and that's when we were looking at angles on a Cartesian plane. And what we did is we said, well, we're going to measure the angle as being from the positive x-axis counterclockwise. So let's do the same thing here. Call that theta. So then you realize, well, wait, if this is the vector, say, AB, let's take something general. Well, again, this is A, this is B, this is the opposite, this is the adjacent. So theta is just given by the inverse tan of opposite over adjacent, B over A. Nice and easy. Okay. This is where things get a little dicey, though, is what if I have a vector that's in the second quadrant, or third quadrant, or fourth quadrant? Well, this is where I'm still going to work. In this case here, I have negative a and b. I'll just represent this as being a negative number, that when I take, theta equals tan inverse of b over negative a. Well, wait a minute. I'm taking the inverse tangent of a negative number. And this is where we realize that my calculator is going to give me an answer somewhere between negative 90 and 0. Okay? If you remember correctly, that when we looked at inverse tangent, when the input is negative, it gives me a negative angle. So that means I'm going to have to do a little bit of work to find the angle from the positive x-axis. In this case here, well, I can say it's going to be 180 and then I'm going to be subtracting, whatever I get here. In fact, I'm going to be adding because it's going to be a negative number. This is going to be 180 plus theta, because theta is going to be a negative number, so it's going to subtract 180. If I'm in the third quadrant, well, I'm still going to find this angle theta, except now in the third quadrant, it's going to be a positive angle. I'm going to have to still do 180 plus theta, because now I'm going to be adding that angle. So you sort of see where this is going. So what this tells me, though, is that, well, finding the angle of these 2D vectors given algebraically is a bit annoying for these directions. But again, what I seem to have implied before is that in order to do all that, those operations that we were doing before, addition, subtraction, scalar multiplication, won't involve having to use this information, okay? And hopefully, it's also going to be much easier than what we had to do before. Remember what we had to do just to add two vectors. You had to set up a triangle, you had to use cosine law to find the length, and use cosine law again to try to find a direction, okay? Hopefully, we're going to get to something which is much easier, okay? So the last thing we're going to do for this week is the magnitude of a 3D vector. But I'm hoping that you recognize this as being something you've already done in this unit. One of the homework questions, one of the assignment questions. In fact, something that you would have done back in grade 9. Okay, you would have solved this problem not in the context of vectors, but finding the length of a diagonal of a rectangular prism, because that's what the magnitude of this vector represents, the diagonal of this prism. And if you remember what you did in that homework question, you realize you would have split this up into two problems. You would have started by drawing this vector here, or back in grade 9, just drawing that line and realizing, hey, I've got a right angle triangle. So if this length here is A and this length here is B, this length is just the square root of A squared plus B squared, the hypotenuse. Okay? And then you would have created another triangle, and you realize that this length is just equal to C, and the side of the rectangular prism is just going to be perpendicular to the base, this rectangle on the base. So guess what you have? Another right angle triangle. Now, it doesn't look right angle, because remember, we're trying to draw a 3D scenario in 2D, but this is going to be a right angle triangle with the magnitude of your vector as your hypotenuse. So if we're looking for the magnitude of u, it's just going to be the square root of the square, sum of the square of the other two sides. So the square of that side plus the square of the other side. But what is the square of root a squared plus b squared? It's just going to be a squared plus b squared plus c squared. And look what we have. A fairly easy formula for the magnitude of a 3D vector. Okay, and it really just looks like an upgrade of that 2D formula that we found. So that's really nice, okay, because they look very similar to each other. Okay, now you notice here I don't say much about the direction of a 3D vector, and that's because we're actually not gonna, we're gonna kind of not spend too much time. I'll just show you what we mean by the direction of a 3D vector, and you'll see why, you'll be happy to avoid it. And the way we define the direction of a 3D vector is we actually use three angles. Is we take the vector here and we say, well, we're going to describe it using the angle to the x-axis, which we call alpha. Then we're going to use the angle that it makes to the y-axis, which we call beta, and the angle to the z-axis, which we call gamma. Okay? Now, because we have to sort of I have to streamline this version of the course a bit. We're not even going to bother seeing how we calculate these. You're welcome to look at it in the notes, okay? But I'm just showing you so that you're aware of what we mean by the directions, what we call the direction angles of a 3D vector. But remember what I was implying before, is that hopefully we'll be able to do all the algebra we need with these vectors without ever having to use these explicit direction vectors. All right, so just a quick recap here. Okay, algebraic vectors, okay, in 2D are defined as the vector that starts at the origin, which I refer to as O, and ends at the point P. So if the point ends at 1, 3, then this is the vector 1, 3. You also notice here that there's an alternate notation for algebraic vectors, and that's square brackets. We're going to use round brackets because that's what the textbook uses, so we'll stick with that. Okay, and remember that once you define the vector AB, you can then move it around because it doesn't change magnitude or change direction. Okay, so we determine that the magnitude of a 2D vector is just the square root of the sum of the squares of the individual components, and for a 3D vector, it's just the sum of the squares of the individual components square rooted. All right? And for the direction of a 2D vector, well, you're going to use the inverse tangent of the y value over the x value. But you're going to have to look at what quadrant the vector is in order to be able to determine the angle from the positive x axis. All right, that's it for this week's lessons.